Now let's take a look at the graph of the tangent and the cotangent function. We'll start with the tangent function, and what we know from previous sections is that there is a relationship between the tangent, the sine, and the cosine functions. That relationship is that the tangent of some angle, in this case we'll call that angle x, is equal to the sine of x divided by the cosine of x. Now, what I want to do to get the graph of this tangent function is actually make a table of values. Instead of giving you the graph like I did on the previous slides with secant and cosecant, I think it might be nice to see a table of values and we actually plot some points because we do use tangent more than we do those other functions. So the table of values that I'm going to use, I just popped up here. We're going to use negative pi over 2, negative pi over 3, negative pi over 4, 0, and then of course the positives of those. Now, what we have is an input, which is an angle, and then the output is whatever the tangent of that angle is, and then of course we will write it as an ordered pair and plot. So I have let the ordered pair be x comma y. That means that my input, or the angle, is x, and my input has to be x with an output of y. Now, let's do the first one. I would have, let me switch pens here, I would have y equals the tangent of negative pi over 2. Now, of course, that's equal to the sine of negative pi over 2 divided by the cosine of negative pi over 2. And what is the sine and the cosine of negative pi over 2? I'm going to pull up this unit circle here for you, and I know that it's small, but hopefully you have this memorized. If you don't have it memorized, then you've got probably your own unit circle that you can refer to. I'm going to start on the positive x-axis, and I'm going to go clockwise pi over 2, and that's going to put me in the same location as 3 pi over 2. So I can see here that the sine is negative 1 and the cosine is 0, and negative 1 divided by 0 is what? Negative 1 divided by 0 is undefined. So my very first ordered pair is actually almost like non-existent, because I can go, when I start to graph this, I can go to negative pi over 2, but how do I graph undefined? If you think back to what we did on the previous slides, you know what happened when the function had values that were undefined. Do you remember that? It created what we called the vertical asymptote, so we should probably expect to see something like that. Now let's try negative pi over 3. And what I would like you to do, instead of me walking and talking through this, why don't you pause the video and fill in the rest of this table and then unpause it to make sure that you've got the same thing as me. Okay, so when I substituted these values in, tangent of negative pi over 3, I got negative square root of 3. That gave me this ordered pair. When I substituted negative pi over 4, I got negative 1. At 0, I'm at 0 over 1, so I'm at 0. So that looks like the tangent function does go through the origin. At pi over 4, I'm at 1. At pi over 3, I'm at the square root of 3. And at pi over 2, I was undefined. So we see undefined not only at negative pi over 2, but also at positive pi over 2. Now, if you've got yourself a piece of graph paper, go ahead and plot those points. I've taken the liberty of already doing that. Let's see if we agree here. Notice we'll start with the negative pi over 2 and undefined. This is negative pi over 2. I've written it as negative 1/2 over pi. That's fine because this is a 1 right here and this is a 1 right here. And so you can see at negative pi over 2 that the red function isn't touching that. In other words, if I do something, let me put this in green, we see here that there is no output at negative pi over 2. So that represents a vertical asymptote, doesn't it? That represents a vertical asymptote at negative pi over 2. Let me jump to negative pi over 4 because that's a nice value. At negative pi over 4, I am down here at negative 1, so that matches. I'm at 0, 0. We talked about that. At positive pi over 4, I'm at 1. And then, of course, at pi over 2, I am also what appears to be at a vertical asymptote. So now let's take a look at the cotangent function. On the last slide, we saw what the tangent function looks like. And what we know is that the cotangent function is the reciprocal of the tangent function, so there should be some type of relationship. All right, now this is a lot to look at, I know. Let's see if we can clean this up a little bit. In purple is the tangent function. So let's just take a look. In purple, I'm going to trace over this for you. Purple, there's the tangent, and here's another one, and here's another one. So the one we saw on the previous slide just had one period of the tangent function. Here is that negative pi over 2. Or negative 1/2 pi. I think on the last slide I said negative 1/2 over pi. I meant to say negative 1/2 pi or pi over 2. And then, of course, also at positive pi over 2, we see the asymptote. For the cotangent function in blue, take a look at this. It is like the same picture, just reflected, isn't it? It's just been reflected. Does it have the same vertical asymptote? Like we saw in the previous slide, we could make a table of values, but we can also just observe that it looks like cotangent has different vertical asymptotes, doesn't it? Looks like it's happening at negative pi, and where else? There's so much going on here. At 0, also at positive pi. So, okay, let's see if we can make a summary here. We know that y equals, I'm going to talk about tangent again, y equals the tangent of x is equal to the sine of x over the cosine of x. And what we also know is that because cosine of x can equal 0, whenever it does equal 0, that's what gives us vertical asymptotes. For cotangent, cotangent is the reciprocal, or we could say cosine of x over the sine of x. And whenever the sine of x is equal to 0, that is when the cotangent function is going to give a vertical asymptote. So now let's take a look at an example. Part A says to determine the domain of y equals the cosecant of x. And to help us with that, I have a picture for us. So let's take a look at this. This is the same picture we saw before. We have the sine function, we have the cosecant function. First, maybe let's answer the question, what is the domain of the sine function? The domain of the sine function is all real numbers, isn't it? I can take a look at all these inputs. I can put anything in there. Of course, the range of the sine function would be from 1 to negative 1. But this one's asking about the domain of the cosecant function. Are there any things that we can't put in? What we normally want to do is we want to assume that the domain is all real numbers. So I'm going to say the domain is all real numbers except what? Well, we talked about this a little bit ago, except negative pi, except for negative 2 pi, except for 0, except for positive pi. And so what I'm going to say is except for integer multiples of pi, otherwise known as 180 degrees. Integers, remember, are just positive numbers and their opposites. No fractions, no decimals. So if we think about 1 pi, 2 pi, 3 pi, negative 1 pi, negative 2 pi, that sort of thing. Now let's determine the domain of the secant function. And there's the picture. And I'm going to say the same thing. I'm going to say that the domain is from negative infinity to positive infinity, except where we see those vertical asymptotes. And that would be at integer, where's that going to be at? Integer multiples of what? Let me see here. So it looks like at negative 3 pi over 2, negative 1 pi over 2, 1 pi over 2, 3 pi over 2. I'm going to say except, I'm going to add the word here, odd integer multiples of pi over 2. Now I had to throw the word odd in there because if I just said multiples of pi over 2, that'd be 1 pi over 2, 2 pi over 2. 2 pi over 2 is not, 2 pi over 2 is the same thing as pi, and I do not see a vertical asymptote. So I had to throw in the word odd, so it would say 1 pi over 2, 3 pi over 2, 5 pi over 2, etc. Of course, that could also be 90 degrees. All right, and 2 more examples for us. Part C says determine the domain of the tangent function, or excuse me, that's C says that, and D says determine the domain of the cotangent function. And there's our picture with both of them on there. I'm going to focus with the tangent function, which is in purple. And what we know from the last slide is that the restrictions on the domain occur at the vertical asymptotes. So I'm just going to go up to that purple graph and I'm going to put arrows where I see it approaching, a certain x value, but not actually getting to it, which is what's making the vertical asymptotes. So that appears to be happening at negative 3 pi over 2, negative pi over 2, positive pi over 2, 3 pi over 2. And so I'm going to say that the domain is all real numbers except, looks like I have that odd integer business again, don't I? Except odd integer multiples of pi over 2 or 90 degrees. For the cotangent, now I'm in blue and I'm going to put arrows up here. These arrows indicate where there are vertical asymptotes, and I'm going to say that the domain is negative infinity to positive infinity, and let's see, where is this happening? Looks like negative pi, looks like 0, looks like positive pi. So except integer multiples of pi, otherwise known as 180 degrees. I don't have to say odd integer multiples because it is 1 pi, 2 pi, 3 pi, so it's not just the odds, it's not just the evens. Now I hope that as I wrote those, you said to yourself, those sound really familiar. Well, that's because I think that they are. For the tangent, you might remember that's the same thing as we saw for the secant, and for the cotangent, that's the same thing that we saw for the cosecant.